Sometimes we may see mold growth or dirt accumulation on a facade, or even damage, like in a timber frame, because of water or vapor leaks. This is because the hygrothermal performance of facade components and material is often not addressed during the design, but in fact is very important. So for this, we're gonna now meet an expert on this topic at URAC Research. Let's go! Thank you very much for welcoming to this lab. Miriam and I are designing a new facade system, and we are approaching the topic of hygrothermal performance. So Miriam suggests to come to see you for some questions. My first question actually is, what do we mean with hygrothermal performance, and why is it important to be assessed?
Yeah, hygrothermal analysis in general is the study of how moisture and heat interact within the building envelope. And with building envelope, I mean walls, facades, or windows, or even a combination of these construction details. And hygrothermal analysis has the main focus of studying how the surrounding environment, namely temperature, relative humidity, driving rain, or solar radiation, can affect these building components and the effect that those conditions can have on the durability of these materials. And so I would say that in general, hygrothermal analysis has a double purpose. On the one hand, to maximize the energy efficiency of the construction details of the building elements, trying to reduce energy losses, and at the same time ensure the durability, making sure that we avoid moisture-related damages so that we don't have moisture accumulation within the construction elements. And typical examples of moisture-related damages that we can have in constructions are mold growth, for instance, which also affects can also affect also the health of the occupants. We can have interior interstitial condensation. We can have material degradation or frost damages, salt efflorescence. So there's a range of effects that we should avoid, and for which it is worth to make a detailed analysis to make sure that we avoid those issues.
When we have interstitial condensation in an insulation layer, for instance, we are also having less performance from the insulation layer, right?
Yeah, that's another issue that I actually forgot to mention. It's like the possibly reduced thermal performance of moist materials. So for this reason, it's necessary to perform those analyses to ensure that the energy efficiency we have planned is actually there.
Because the material is dry.
Yeah, it's dry and yeah, for sure, yeah.
This makes me think that we are more aware of simplified assessment like glacier, but probably, as you were saying, it's a much more complex physical phenomenon. More detailed analysis might be needed to really fully characterize the performance. How do you perform this analysis?
Yeah, I mean, there are several types of approaches to this kind of analysis. And yeah, I would say that one of the key approaches that we use is for sure numerical simulations. And here what we use are numerical simulations that are hygrothermal simulations in dynamic regime. And as you were mentioning before, this goes far beyond simplified methods based on the Glaser approach that you were mentioning before, for a number of reasons, actually. Glaser, first of all, is a stationary method and not dynamic. It means that the boundary conditions are stable and are not changing like it is in reality, while in the hygrothermal simulations we perform a calculation on an hourly basis or even sub-hourly basis, having really a detailed description of reality. And on top of that, in hygrothermal simulation, we model the combined transport of moisture and heat into the construction, and we can include all the relevant physical effects that occur in reality. This is vapor diffusion, for instance, that is also included in the Glaser approach. But we model also the liquid transport by capillarity, which, for instance, this is neglected in the Glaser approach, and also moisture storage that is also neglected in the Glaser approach. So we have a much more accurate description. And on top of that, we can model also two-dimensional or even three-dimensional details that also in Glaser is not possible. So we go way beyond that, and also model the coupling with all basically relevant boundary conditions, which include temperature, relative humidity, rain, as well as solar radiation. So we have really a detailed description of reality, which aims to really get an exact description, an exact modeling, which is far beyond what Glaser does, which is instead a simple assessment method, I must say.
So if we have all these complex assessments, why do we need tests? Why we are in a lab?
Yeah, typically complex assessment means also that you need a lot of input parameters that are very crucial to get correctly in order to have a right description of reality. And actually the material properties are very important to measure. It's one of the key input parameter of our agrothermal simulations. And that's what we're doing in this lab, in the agrothermal testing lab at EUROC Research. We measure the agrothermal properties of the material, and that means how the heat and moisture are stored and transported by those materials. And as I was saying, this is a key input parameter of the simulation, and we need to know it in order to get reliable results. Otherwise, we might get very wrong results. So it's really a crucial aspect. And also, it is important to have a comprehensive set of parameters. So that's why here we have all the equipment needed to measure a number of parameters, which includes thermal conductivity, specific heat capacity, vapor permeability, liquid conductivity, and moisture storage function.
So this means that, first of all, it's very important to do experiments in the lab to characterize and being able to describe appropriately the agrothermal behavior of the material. Yeah. Was this the case of these materials?
Yeah, that's an example of two materials that we've been measuring in the lab, and those are two types of insulating plaster, and they are insulating because they are made lighter thanks to the addition of this expanded glass or this aerogel, which is actually one of the lighter material and more insulating thermally material on Earth, actually. And actually these have been added to a lime plaster to be able to design a material which is a thermal insulating plaster. That's the way in which it's called. And we study in detail in this lab because we wanted to study its application as interior insulation, where not only it is important to have information on the thermal resistance that the material adds, so that means how much it is insulating the wall, but it's also important to make sure that we avoid interstitial condensation and moisture accumulation. And actually this material is called sometimes capillary active insulation material, because thanks to its ability to transport water in liquid form, it can avoid the moisture accumulation and the interstitial condensation. So that's a little bit why it is important really to study the properties in detail.
And without this?
And that's another example of material. Is a membrane, as you can see. It's called a moisture adaptive membrane, and it has a very peculiar property it is changing its vapor permeability depending on the humidity of the surrounding environment. And in particular, if the surrounding environment is humid, this becomes a very permeable material. So if a construction is wet, it can dry out. While if the surrounding environment is dry, it becomes a vapor retarder, and so it prevents that it gets wet. So it is often used as a vapor control layer, and since it has these properties that are very peculiar, they also need to be studied quite in detail, and that's what we did here in the lab. And then we studied a potential application as a vapor control layer in flat roofs and again in interior insulation systems.
And is this then simulations, tested in the lab? is there also the need sometimes to go and do some measurement in a real building?
Yes, making on-site monitoring in real buildings is also another type of approach for agrothermal analysis, and I would say is really important also for validation purposes, because one can get the final confirmation that everything works correctly, how it was designed, and how it was thought to perform. And it is really typically you place some sensors within the construction in real buildings in points that are expected to be the most critical one, and then you monitor the real-time behavior typically of temperature and relative humidity, and it is a very powerful tool. You don't have to go through a modeling, so you're sure that you're really observing reality. So this is definitely the advantage. The disadvantage in this case is that it's very expensive to implement typically. It's not something that can be done systematically in all projects. And also you can verify the performances only once the solution has been designed and implemented. So it is typically used, as I was saying, in combination with simulation, where you predict something and then you verify whether it works as predicted. And so it is typically a combined effort and is used for validation purposes.
Oh, thanks. I think now, Miriam, we have almost all we need to do our analysis.
I think so. Thank you.
Thank you very much.
Thank you very much.